You know that story we were all told as children about a giant asteroid that struck the Earth millions of years ago and wiped out the dinosaurs?
Vaguely.
We were wrong. This metal caused the Great Extinction.
You have no idea what's been happening here. We're about to make the quantum leap.
It's the Holy Grail. Transformium. That's what we're calling it. This is the greatest advance in modern physics. It's a programmable matter.
Now we can begin to give it instructions.
Inventing the Future with Robert Tursick.
Hi, good evening. Thank you. Are you ready for some adventures in synthetic biology? You're going to learn some amazing stuff. This is absolutely at the forefront, the cutting edge of science right now. It's not your grandfather's genetic engineering in the sense of taking two genes and splicing them together. This is a radically new notion. People are actually composing life. What they're doing is they're writing DNA, and they're writing it the same way that a software developer would write code for a computer. Except in this case, they're writing DNA that's then put into a living thing and can replicate, and can replicate. Hi, and welcome. Ooh, thank you. Trick each other. So welcome to Chicago, where it's freezing cold. You just joined Autodesk, and I want to hear all about this. So tell me what your new title is.
My title is Distinguished Research Scientist with the Bio-Nano Programmable Matter Group at Autodesk.
That's a mouthful.
It is.
Basically, the stage we're at with synthetic biology is the same stage that we were with personal computers back in the late 70s.
Absolutely.
Where people were, it was like homebrew computer club. People were building their own computers in their garages or their dens. Kind of like the labs that I was talking about a minute ago.
Exactly, except now we're working with a different type of computer, really bacteria. They're like information processors that do chemicals, but they're different. They're programmable, but the cool thing is they also make more of themselves. So they're like computers that can reproduce. This is pretty powerful.
That's amazing.
And if you look at a bacterial genome, it has about 5 megabits of information. Really, a small photograph. But this is enough to program a living thing. And really, if you've got a software program, you have to learn the basics. You have to learn how to read it. You have to learn how to write it. Right. We've been sequencing with devices like this. This is a desktop. It's about the size of a laser printer, but it can do a whole human genome. And reading it, we're starting to comprehend more and more of the basic tools of life, this is a simulator for the first bacterial cell. It's actually
what's
really
going
cool.
on? What is this a picture of?
We're actually modeling all the chemical processes that happen in a single bacterium and understanding what's going on below the hood.
So this is a computer model of a cell.
Computer model of a living cell.
Wow, that's incredible.
It's the first time we've ever done this. This was published by Stanford this last summer. And really what we're doing now is we're starting to learn how to write code.
Thanks.
We started writing genetic code back in the 1970s using something called recombinant DNA technologies. It was cutting and splicing genetic code. And really, if you take a look at it, you end up kind of writing ransom note style. You can write anything, but it takes a long time to do. The shift with synthetic biology, and what makes it so powerful, is now we can actually use computer software. We don't need a lab anymore. We don't need these tools, which are really restrictive. We can start using laptops.
So they virtualized the lab.
Yes, essentially now we have word processors for DNA. And the cool thing is we have printers. Companies like DNA 2.0, and there's a bunch of other ones, will print out your DNA, kind of like a Kinko's used to, prints out color copies.
So the analogy to the computers is actually total.
It's really close.
So the idea, in the 80s when personal computers got good, we went from desktop, word composition to desktop publishing, and that was a big change in the print business.
Now we're getting desktop biotech. And so it's
unbelievable.
push-button DNA, and this is...
So you can compose DNA using a browser.
You can compose DNA using a
you
browser.
you
can
hit a button and
print.
send it.
They'll send it off to you.
That's awesome.
And this is opening up biotechnology to a whole new generation of people that are younger and know how to work with computers in the same way that 30 years ago kids started playing with personal computers.
And this is a big part of what you're doing. When I first met you, we were in Silicon Valley, and you were telling me that you've been working with high school kids and even grade school kids to try to get them to learn about synthetic biology, to maybe give them the confidence to play with it and experiment.
Yeah, I want them to realize this is potentially going to be a field that they will work in for the rest of their life if they start getting interested in it.
And how's that going? I mean, do kids respond to this
It's
stuff?
going really well. Really, some students naturally pick this up, and they love working with it. And
So they don't see a big barrier. The way, I think when I was a kid, biology was for geeks. It was a challenge. You had to go, had to wear a lab coat, and you had to
Exactly.
schedule time, and there were beakers involved and so on.
yeah, it was more sciencey back then. Now it's more of an information science.
That's cool. And then do they use these things, like when you work with kids, do they use Genome Compiler to go print out their organism or their DNA that they develop?
They certainly use these types of software tools and these DNA printers routinely now.
That's kind of cool.
Yeah, it's really sharp.
Take us a little bit into the future. So tell us what's coming next then with this.
Well, really what's been happening is we're starting to move into modularizing this type of genetic code, making it easier to assemble and to put together faster and cheaper. It's kind of like Lego bricks. It's really extensible. And the groups that's driving this forward is out of MIT. It's called International Genetically Engineered Machines. And it's really it's really the best student program for learning how to do synthetic biology.
Hang on a sec. So it's genetically engineered machines. So they're thinking about life as a kind of like a robot or a machine that you can control.
Yeah, we look at simple bacteria as really being little robots that are programmable.
So that's a little bit different from, in the opening comments, I talked about people who are building labs in their houses, in their dens, or their closets.
There's definitely a few people that have done it.
In a way, we're moving away from that now, where you can go join, it's like joining a hackerspace or a maker community.
It's more fun when you do it with a group anyway.
Sure, and you can get your questions answered, or somebody can show you how.
Exactly, and you don't have to worry about the FBI necessarily beating down your door. So, and the groups that are really getting good at this, well, they're using robots to do not just printing of DNA, but actually booting of the organism and testing. So this is allowing people to really have biotechnology done remotely. Really,
wow,
just
that's cool.
Send a design, they'll build and test.
That's a big one. So hang on, that means you could design an organism on your desktop computer, your laptop computer at Starbucks even, and then send it out to get not just printed or not just have the DNA compiled for you, but you could actually have the organism made, manufactured, produced. What verb do they use?
And the results come back to you, and you can decide whether you're going to.
So if you didn't get it right the first time, you can do it again.
Do it again.
As humans, we create hundreds of millions of tons of waste every year, and a lot of it is this PET plastic. As Chief Creative Officer of 3D Systems and co-founder of EcoCycle with Coca-Cola, I've created a solution, the EcoCycle Cube 3D printer. This machine prints in post-consumer plastic. That means you could take this water bottle and print bracelets, robots, vases, shoes. That means taking this waste and not wasting it, and turning your ideas into beautiful objects printed in this 3D printer. Welcome to the future.
Introducing Droid DNA by HTC. It's not an upgrade to your phone, it's an upgrade to yourself.
Welcome back. Sorry with Lady Gaga. Born This Way is the new single. Tell us about the album.
Oh, I love the album so much, and I hope all of the monsters do too. And the performance we did last night at the Grammys was, and what we've been doing with the egg and the rebirth. It's meant to signify an artistic statement of birthing a new race, and it's a race with no prejudice, a race within the race of humanity that bears no prejudice against anyone. So that's really the statement in itself.
Good evening. I'm Dan Atkinson. I'm the Director of Public Programs for UC San Diego Extension, and it's my pleasure to welcome you for this evening's talk with Dr. J. Craig Venter.
Thank you, and good evening, and welcome. Although Dan said it will be an interview, it won't. It will be a conversation. We don't know where it's going to go. But then, that's kind of been your life, hasn't it? Craig Venter, let me just briefly say, founder, chairman, and CEO of the J. Craig Venter Institute, also founder and CEO of Synthetic Genomics, and also a recipient of the United States National Medal of Science. We're here because he has a new book out called Life at the Speed of Light, From the Double Helix to the Dawn of Digital Life.
So the thesis of the book, going through everything, is that the DNA world and the digital world are becoming rapidly interchangeable. When we read the genetic code, I describe it as digitizing biology. And we've been doing this basically since Sanger's sequence of the DNA virus FIX174 in 1977, and up through the human genome and then well beyond, we've been filling the databases with digital code that describes the DNA code. And now we can go the other direction.
The reason that I mentioned that was that what you're talking about is re-engineering the genome in a much more logical fashion. Yeah. In other words, you're saying there is a better way of doing it.
Yeah. Evolution is really messy. So all these people that want intelligent design need to look to the future, not to the past. And so we're actually thank you. I think Ham Smith on the team came up with the notion, we're defragging the genome by taking this messiness away and organizing genes by function in a logical way, because if we're trying to do design, you want to have cassettes for energy metabolism, cassettes for replication, etc. And so we're trying to redesign a cellular genome in a logical fashion for this future phase of evolution that we're now entering.
shape-shifting material that can transform itself in real time, changing colors and shape on demand. It sounds like special effects you would see in a sci-fi movie, but this is no illusion. Researchers at Intel teamed up with the academic community to make what they call programmable matter.
The basic idea is the notion that you could have a material that could change its shape or change its physical properties just by reconfiguring itself.
Forget about designing something in flat 2 dimensions. What about creating a 3D prototype of anything, even a car?
Open the doors, kick the tires, peek inside to see what it looks like, fit little dolls of, people inside of it.
This space-age stuff is like putty in your hands. Programmable matter is still in the early developmental stages. But Intel's Andrew Chin says one day we may be able to morph objects on demand to fit our human needs.
So for example, I have a Bluetooth earpiece and it fits me great, but then when I put on my sunglasses, it doesn't fit anymore. Wouldn't it be nice if it could change its shape subtly, right, to all of a sudden match that? All of these things are possible with programmable matter. We are definitely on the edge of discovery with this one.
Gary Tuckman, CNN, Atlanta.
Wait. What are we playing here? Retard bingo? What? That was on the table from the start.
Forget the start. It's the end you want to think about now.
This is a world that doesn't play by your rules. Like it or not, you and your friends are a part of it now.
I don't have friends. I got family.